Welcome to a new problem solving session, and in this session we will be discussing cases or applications of conservation principles, namely mechanical energy conservation, linear momentum and angular momentum conservation in rigid body mechanics. Right now we have a very logic problem at hand, and I think this could be the application of mechanical energy conservation. So let's read the transcript of the problem so we can be able to move further. There are two identical small metal balls, you can see here by yourself, to the ends of a light rod of length L. Okay. The rod is placed on a cube-shaped stand, right, of edge length small l, which is very much smaller than the length of the rod. And the rod midpoint is above the midpoint of the upper edge of the stand. Midpoint, that should be at a distance L by 2 and a small L by 2, and this length could be L by 2, capital L by 2, and this is capital L by 2, though it doesn't seem like that, but this seems to be the statement of the problem. So and then deflected by a small angle. I think it is deflected. Okay, it is already deflected by an angle, by a small angle phi naught, that is very much small. I can see it is very much smaller than 1 degree. That means it's quite a small angle. Then determine the time taken by the rod to switch its position from the left to the right corner. Oh boy. Left to the right corner, provided it does not slide over the stand. Thank God. That means friction is absent. Sliding friction is absent. That means we can safely use mechanical energy conservation. But why mechanical energy conservation? Why not net torque equal to I alpha? Why not equation of moment? Because somehow we will be needing its angular acceleration as well to solve this problem, because we have to find the time taken. But the torque thing is, I think, not very much fruitful in this case. So let's focus on the problem. It does not slide over the stand, and the energy losses when the spoke, that means rod, switches from one edge to another are negligible. Okay, that means the statement of the problem is strongly suggesting us to use the mechanical energy conservation thus. But let's do something to this figure. It doesn't look good, so I have drawn another here. And if the statement of the problem is clearly hinting us to use the mechanical energy conservation because there are no energy losses, there is an absolute absence of sliding friction, so we are going to use it. And where is the midpoint of the rod? Suppose that this is at this point and it is right above the center of the upper surface of this cube. So this length is going to be L by 2, and for time being it's going to rotate about an axis, passing through this point, passing through the left corner of the cube, and it is going to rotate like this. So that's right. That means phi naught has changed, and now the angle becomes something like phi. So its angular velocity can be written as d phi by dt, and if it has got some kind of angular acceleration, we can write it like this: d2 phi upon dt square. Now what? Now mechanical energy is conserved. That means kinetic plus potential energy is conserved. So I need to write down the kinetic energy and potential energy of this system, rod plus ball system. Rod is light, so it doesn't contribute either to the kinetic energy or potential energy of the system, but the balls will. Balls are not massless, and let their masses equal to m. It was shown in the problem. Okay, their masses as m, and so the system has got rotational kinetic energy. As you can see here, it is rotating about fixed axis, an axis passing through the left corner of the cube. So it's a case of rotation about fixed axis. So we're gonna need to write the rotational kinetic energy of the spheres. So I'm going to write kinetic energy equal to left rod, that is half I omega square. I means moment of inertia, and moment of inertia of this small ball, its size is negligible, so it can be treated like point. So its moment of inertia can be simply written as ml square, and to do so we will be needing this length, and we have information simply that this length is L by 2. So we need to find out this length, and this length must be subtracted from L by 2 to get the distance of the left ball from the axis of rotation. And this angle is phi, so we have a right angle triangle and a cos phi situation, that is simply L by 2 upon, let's call this length d. So it is base by hypotenuse. That means d is L by 2 cos pi, and phi is very small. This phi is even smaller than phi naught, which was already very much small. So this phi must be very small. That means we can approximate cos pi with 1. And the value of cos pi we are going to, operational value of cos pi we are going to put here is 1. So this length d is simply L by 2, a small L by 2. So the distance we are looking for, this distance is going to become, this distance is going to become capital L by 2 minus a small l by 2. So let me write the moment of inertia, that is mass L minus L by 2 square. This is the moment of inertia, half I is completed. And now I'm going to write omega square. Omega is d phi by dt, so d phi by dt square. So left rod got completed everything, and in the similar manner we can write for the right sphere, left rod, left sphere and right sphere, and in the similar manner we can write for write the expression for kinetic energy of the right sphere, and that will be half m, and distance I guess it will be L plus L by 2 square, that is the moment of inertia, multiplied by omega square, that is d phi by dt square. So but we need to make some approximation as well, because there was a condition saying L is much less than L, so we need to use this information as well. So let's manipulate the things. Half m d phi upon dt square is common. So we got what? We got 1 by 4 L minus L square plus L square. So, and it's becoming messy, but half m d pi by dt square 1 by 4, this becomes 2ll, I think gets cancelled, and we can get something like here 2l square plus l square thing here only by calculating these two things. And so we have final expression like m upon 4 L square plus L square multiplied by d phi by dt square. And since small l is much less than capital L, so its square can be neglected, and we can write the expression as m L square upon 4 d phi by dt square. And this is the kinetic energy of the balls in pure rotation spheres. Now we need to write down the potential energy of the system. So how can we write the potential energy of the system? This ball is at some height, yes, and this gravitational potential energy. So we will be needing this length, because I am going to take the zero potential energy level at here, that is called datum or something. If this angle is phi, this angle is phi as well, and this length is L minus L upon 2. So this length will become L minus L by 2 sine phi, and phi is much smaller than 1 degree. So instead of sine phi, we can simply write phi. That means sine phi can be replaced by phi. Okay, so we got what? L minus L by 2 phi, and for this will become L plus L by 2 phi. So we are going to write down the potential energy of the balls as well, and this will be minus mg for the left. It is below the datum, so I'm going to write down minus mg L minus L by 2 phi, yeah. And for the right, it will become plus mg L plus L by 2 multiplied by phi. This is the potential energy. And at this moment, but I need the time as a final product, so I need whatever the acceleration, angular acceleration of this rotating system or something like that, and we don't have it. So I'm going to do one thing. I know mechanical energy can be written as the total mechanical energy can be written as kinetic energy plus potential energy, and if it's a constant, then dE by dt is equal to 0. And derivative of any constant with respect to time must be equal to 0. So I'm going to write down the potential energy. Kinetic energy means total mechanical energy means kinetic energy plus potential energy, and kinetic energy, you can see here, it is ml square by phi d phi by dt square. Okay, and potential energy is something I haven't solved this, but minus mgl by 2 plus mgl by 2, and this minus gets plus. We can calculate it, and it comes something like mgl phi only. This thing can be brought to this thing, not by approximation, but by simply manipulating the things. Open the brackets and you will get something like that. This, so potential energy become mgl pi, and we need to differentiate this. I'm going to put dE by dt equal to 0. So that means it will be ml square by 4 2 d phi by dt d2 phi upon dt square plus mgl d phi by dt, and that is equal to 0. Now what? I can see d phi by dt can be taken as a common from left side, and since it is not equal to 0, we can divide by it to the 0 of right side, so that it becomes 0 the whole thing, and we can write something like ml square by 2 d2 phi upon dt square, it is equal to minus mgl. So m gets cancelled out, and not more than that. We can simply get from here that d2 phi upon dt square is minus 2gl upon l square, and now it's time to find we are going to find out the time taken. So I'm going back to the problem, and determine the time taken by the rod to switch its position from the left to the right corner. But before going to right corner, it will become horizontal. The system will become horizontal, and then it will go to the right, and I guess in the same manner, again making angle phi naught if this is the equilibrium position. This is not explicitly mentioned in the problem, but how can I find the time if I don't know? So I'm assuming that this thing is going to happen. It again, the rod ball system makes an angle phi naught from this side. So I'm going to find out first the time taken from this position of the rotating system to its horizontal position. And if this time is something tau, then our answer will be 2 tau, because it will take the same time to move in the same manner to come in the same position. So I'm locking this problem, that I have assumed that this thing was asked in this problem, and the answer is going to be 2 tau, where tau is the time taken by this rod to become horizontal. And so I'm going to solve the rest of the credentials. You can see here d2 pi by dt square, the angular acceleration, is a constant here, and the problem is potentially worthy of to find a complete time period, but let's forget it for time being. This 2g small l capital, I don't see a variable here, so it's a constant. That means it's a uniformly accelerated motion time, so I can use s equals ut plus half at a square. Initially it was at rest, so I'm going to use half at a square. So half at minus 2gl upon l square into tau square is equal to the displacement, and displacement is minus phi naught. So it was initially rotated to an angle phi naught, and then it becomes 0, so its angular displacement is minus phi naught in this time interval tau. We get the value of tau from here, and it is something like phi naught upon gl. 2 gets cancelled out, and capital L can be taken out of the square root because it is already a square. So the tau is simply g naught, not g naught. In fact, this is phi naught upon gl multiplied by L. And we have the answer that will be equal to 2 tau, and that's the answer. That's the final answer. And if it completes a full cycle of motion, rotating about left corner to become horizontal, then it will again rotate to the right corner, and it is going to stop at an angle phi naught because its angular acceleration is constant, and then will again rotate to the horizontal, and then it is again going to rotating and moving to an angular position of phi naught about the left corner, and then it completes the full cycle. In that case, its time period to complete the full cycle will be 4 tau. So thank you for watching.